Greetings and welcome to the complete lecture for what I call Chapter 7, Part 2 of Chemistry 222, and I'm really glad to have you here. Now, at the end of Chemistry 221, we looked at the beginning of Chapter 7, which was section 7.1 to 7.2, and in Chemistry 222, or Chemistry 222Z, you should definitely kind of look those over to make sure that you're up to speed with all that stuff. But what we're going to do in this new section is we're going to really look at the power of the chemical equation, and we're going to see all the different things that a scientist can do to figure out how many reactants we need, how many products will be made, or if you want so much products, how many reactants you'll have to put in to make it happen. It's a real powerful chapter for chemists. It really shows the power of chemistry and what chemists can do and why people want to pay chemists for that matter too. So without further ado, let's check this out and see what this section has to offer. Section 7.3 of this chapter is entitled Reaction Stoichiometry, and stoichiometry is a fancy name that I will never make you spell, by the way, because it's kind of weird, but it's basically the study of quantitative aspects of chemical reactions, which is really related to amounts, like how much do I need to make this much, etc., etc. So stoichiometry is really the study of measurements and how much you need to make something happen. So in chemistry, what's really important here is that we use stoichiometry in relationship to the conservation of matter, which just says that all matter that goes in has to equal the matter that goes out. You can't lose or destroy or create, for that matter, any matter. It has to be accounted for. And we use the balanced chemical equation to figure that out. So in the lower right-hand corner there, that's a balanced reaction, which we talked about at the end of Chemistry 221. In that reaction, we're taking two solid pieces of aluminum and reacting it with three gaseous pieces of bromine, Br2, to make two solid pieces of aluminum bromide, AlBr3. The 2, the 3, and the 2 are called the stoichiometric coefficients. They tell you relative amounts. Now, I use pieces and things like that in the last description. You probably know that this is going to be the mole in chemistry. So in chemistry, we would say that you need 2 moles of aluminum to react with 3 moles of bromine, and that will create 2 moles of aluminum bromide. Notice that 2 plus 3 on the left side do not equal 2 on the right side. The big stoichiometric coefficients do not equal each other on the other side. But what does equal, and what's important, is that the left-hand side has 2 aluminum atoms and the right-hand side has 2 aluminum atoms. And the left-hand side has 3 times 2, 6 bromine atoms, and the right-hand side has 2 times 3, 6 bromine atoms. So the atoms are balanced, even though the stoichiometric coefficients may or may not be balanced, and that's something to remember. Also, instead of calling it left and right, let's call it by the official names. The left-hand side are the reactants, and the right-hand side are products. And those little things in parentheses to the right of the chemicals, those are the states of matter. They're not always included, but they can be very helpful. S means solid, G means gas. You'll also sometimes see L for liquid, and also you might see AQ for solutions. So that's kind of a very fast overview of a lot of the last chapter of Chemistry 221, and we'll talk about it more here coming up. As always, if you have questions on anything from Chem 221, because I know that was so long ago now. No sarcasm, honestly, I kind of feel that way myself sometimes when I'm starting a new term, but anyway, that's a personal problem. You don't need to worry about it. Oops, I'm recording it. Okay, anyway, if you ever do have questions on anything, I'm happy to help you, okay? Don't lose any sleep about it. There are no dumb questions in my class. Some of my answers, you may need to ask the question again to get a good response, but your questions are valuable to me, and I'll do my best to answer them. Chemistry is kind of like cooking. A chemical reaction is kind of like the recipe up there at the top middle kind of to make a pancake. And you can see that it says a cup of mix and 3/4 milk and an egg makes 8 pancakes. All right. Woohoo. Well, if you're hungry, that can be really important. In the lower left-hand corner, there's like another recipe of sorts where you have flour and sugar and oil and chocolate and eggs, and somehow that makes a cake. Fantastic. You can cook just about anything if you put your heart to to it. And in chemistry, you can make just about anything too, as long as you follow the instructions. So you do need to know how much to add. So for example, in your cake, if you had too much flour, it wouldn't come out very nice. On the other hand, you added too little flour and it would come out kind of weird and hard and stuff like that. So you have to know the amounts and stuff in cooking, and you have to know the amounts in chemistry. If you're having people over for dinner, it's nice to know how much you're going to make. So if you're making one cake and you have, say, 6 people or something, 8 people, I don't know, that would be fine. But if you have 20 people coming over, you might need, for example, 2 cakes. So it's nice to know how much you're going to make, how much you need to put in. In chemistry, in addition, that doesn't usually happen in the kitchen, but it can be. Chemistry can be dangerous, all right? You can have an excess amount of energy released, or all kinds of things can happen. So there's a lot of reasons for paying attention to a recipe. There's a lot of reasons for paying attention to something in the chemistry lab. And this is what we're going to try and conquer in this section. So this is a flashback to Chemistry 221, and I want to talk about the important ingredients in a chemical reaction. And this is another example of a chemical reaction. This is aluminum and oxygen making aluminum oxide. So you can see, first of all, that there are some diatomics. Aluminum is not a diatomic, but oxygen is, so that's why it gets a little 2 next to it. And also, those stoichiometric coefficients, really cool. And again, 4 plus 3 does not equal 2. That's okay. But the atoms of aluminum on the reactant left side equal the atoms of aluminum on the product right side, and the atoms of oxygen, 3 times 2, 6, equal the atoms of oxygen, 2 times 3, 6, on both sides. So it's the atoms that are balanced, but not necessarily the coefficients. Those coefficients are super important, though, we're going to see in a little bit, so just hang on. You might see, like I said earlier, solid, gas, aqueous, and liquid. Those stand for the states of matter. They're not always there, but it can be really helpful. And again, it's not the coefficients that are balanced, but it's the atoms that are balanced. This is the law of conservation of matter, sometimes called law of mass action. And you've got to pay attention to that if you're going to have any success in the things we're going to talk about here shortly. Now, for this reaction where 4 aluminums react with 3 oxygens to make 2 Al2O3s, that reaction implies all of the following ratios. And there's a whole bunch of them. So let's talk about the first couple ones. In the upper left-hand corner, it says 4 moles of aluminum for every 3 moles of oxygen. And it's not like magic where this all came from. The 4 came from right there by the 4. That's the 4 moles of aluminum. And the 3 in the bottom is the 3 right there, 3 moles of oxygen. No problem. So you can see the one right to the right, 4 moles of aluminum, 2 moles Al2O3. You can see where that ratio comes from. But sometimes it's nice to have the opposite ratio. So let's flip the 4 moles Al for every 3 moles O2. We would then write it 3 moles O2 for every 4 moles Al, etc., etc. So from this reaction, we get those 6 ratios, and those ratios are really, really important. It's a stoichiometric ratio between reactants and products, products and reactants, reactants, reactants. Anything is possible, but it comes from the power of the balanced reaction. Like all good conversion factors in dimensional analysis, you can flip them on their head. So you don't want 4 moles aluminum over 3 moles O2. You can flip it. 3 moles O2 over 4 moles Al. No problem. That's where these ratios become so important to chemists, because it allows you to go from one reactant to another, from a reactant to a product, from a product to a reactant, or a product to a product. And I'll show you some examples of this here coming up. Here's a reaction. Let's say that we have nitrogen and hydrogen reacting to make ammonia, NH3, and we're mixing 10 moles of H2 with an excess of nitrogen. What stoichiometric factor would we use to calculate the moles of NH3 produced? Okay, so in the naming of this, in the language of this problem, it says 10 moles of H2 with an excess of N2. So that means we have more N2 around than we know what to do with. So we're going to try and convert, in this case then, moles of hydrogen into moles of ammonia. So we're starting with 10 moles of hydrogen. That's like the top part. So we could write 10 10.0 moles of hydrogen. And we want to convert this into moles of NH3. So by the H2 there's a 3. So I'm going to put 3 moles H2 on the bottom. And we want to turn it into ammonia. There's a 2 right there. 2 moles NH3. So the ratio we're going to use here then is the bottom one. It's 2 moles NH3 for every 3 moles H2. Now I hope you're kind of seeing here what's going on. We're going to want to convert how much hydrogen we have into how much ammonia we can create. And you can see hopefully here how the moles of H2 on the top and the moles of H2 on the bottom are going to cancel. That's going to allow us to calculate the moles of NH3 that we can create. So in this problem, if we would multiply 10 moles by 2 over 3, we would get 6.7 or whatever. That would be the moles of NH3 that we can get from this reaction. So that's where these stoichiometric coefficient factors come in, and that's where having a balanced equation so important for chemistry. So here's another kind of question you might see. It says, what mass of sodium hydroxide would be required to produce 16 grams of magnesium hydroxide by the following precipitation reaction? Okay, so this is another little thing we talked about in Chem 221 at the end. A precipitation reaction is a type of reaction where the like parts are trading places. So magnesium and sodium are both positive metals, cations. They're going to swap places. Now magnesium was positive 2 on the reactant side, and it's going to be positive 2 on the product side. And if it's going to start dancing with hydroxide, which is a -1 polyatomic ion, the formula then will be MgOH2. Now in the process, Na is going to start dancing with chloride to make NaCl. We'll balance the atoms and put a 2 in front of the NaOH and a 2 in front of the NaCl and be good to go. But also what we can do here, most hydroxides are insoluble. So that means we need to put an S by them. The only time we do is when the hydroxide is next to sodium, potassium, lithium, the group 1A cations. No problem. And chlorides are usually AQ. Sodium is always AQ. So that's why there's the 2 there by the NaCl. So again, if you have questions on this, let me know. But what we're going to do here, we want to figure out how much sodium hydroxide, NaOH, we need to produce 16 grams of magnesium hydroxide. And what the balanced reaction is going to give us, it's going to give us a mole ratio between MgOH2 and NaOH. So if we can turn the grams of MgOH2 into moles, we can then use the balanced equation ratio to go from moles of MgOH2 to NaOH, and then finally, since we want mass, which is grams, we'll turn the moles of NaOH into grams using the molar mass and be good to go. So let's see what this looks like then mathematically. So we're going to start in this case with 16 grams MgOH2, and we need to turn that number into moles of MgOH2. Now that 58.3 number is the molar mass of MgOH2. If you take a magnesium, which I think is like 24.3, and add oxygen about 16 and hydrogen, which is about 1.0, you're going to get 58.3 grams per mole to the 10th position. And that allows us to go from grams to moles of MgOH2. But the new part now is this in the middle. And this is that ratio I was talking about. There's an invisible 1 by the MgOH2. Chemists don't usually put 1s. They'll put 2 and greater. 1 mole magnesium hydroxide needs 2 moles NaOH. That's where the ratio came from. And that allows us to turn the MgOH2 into NaOH. Finally, then, we're going to turn moles of NaOH into grams using the molar mass, add up a sodium, an oxygen, and a hydrogen, and it's about 40.0 grams per mole. 2 significant figures is what we want right here because we put 2 sig figs in, 22 grams NaOH. Now imagine the power of this just for a second. Your boss says, hey, we need 16 grams MgOH2. How much NaOH do we need? You just calculated 22 grams, and that's what you can tell your boss, and that's what will allow you to get the 16 grams out, which is kind of cool. So I call this sometimes the grams, moles, moles, grams dance. It's not really a dance, but it kind of feels like it. And what you're doing, you're turning grams of your starting material into moles, like we did MgOH2. The moles to moles part comes from the balanced reaction, which you just need to balance and figure out. And then you go back to grams, the moles to grams part, using the molar mass of what you're looking for. We'll do this a lot. It's not hard or anything like that. Make sure you're hip how to get a molar mass value from the periodic tables, and you're good to go. Here's another example of a problem very similar to what we just did. And in this problem, we're also going to use the grams to moles to moles to grams dance thing. Sorry, your instructor has a strange sense of humor. But anyway, let's say that we're going to take 1 pound, which is 454 grams. And I didn't even put up pounds there because we don't want to use American units if we don't have to, basically. But anyway, 454 grams of ammonium nitrate. And we're going to decompose it. And the question is, how much N2O, dinitrogen monoxide, and water, H2O, will be formed. And also you can see there I tacked on what is the theoretical yield of the products, which we'll talk about here in a little bit. Okay, well, before you start a problem like that, you've got to have a balanced reaction. And at this point, we know that NH4NO3 is going to be the reactant, and it's going to break down to N2O and H2O. So when you look at those long enough and you balance it, you'll see that there's going to need to be a 2 in front of the hydrogen. NH4NO3 has 2 nitrogens, 4 hydrogens, and 3 oxygens. And you can see on the product side there that with a 2 in front of the water, you have 4 hydrogens, there's 2 oxygens in water, and another oxygen and N2O for 3 oxygens, and N2O has 2 nitrogens. So that's the balanced reaction. Very, very important. The next thing we're going to do, we have to turn the grams of reactant, ammonium nitrate, into grams of product. This is going to be grams, moles, moles, grams. Now you've got 2 choices here. You could do water or N2O, and it honestly doesn't matter. In this example, I'm going to do water first. So what we're going to do, we're going to turn grams of ammonium nitrate into moles of ammonium nitrate using the molar mass. We're then going to use the balanced reaction to have 1 mole NH4NO3 to 2 moles water. So what that's going to look like, 2 moles of water on the top, 1 mole NH4NO3 on the bottom, and that'll allow us to go from moles of reactant into moles of product water. Then we can take the moles of water, turn it into grams of water using the molar mass of water. Pretty chill. So here's what this looks like, all right? What this is going to look like, we're going to start on the left there, 454 grams of ammonium nitrate. And when you figure out the molar mass of ammonium nitrate, it's about 80.04 grams per mole. And check this out. Make sure you can do this. This is a Chem 221 thing, but I don't want that to stop you here in Chem 222, so make sure you're good. That'll allow us to go grams of reactant into moles of product, moles of ammonium nitrate. Now this next part, the 2-to-1 ratio, it's not magic. 2 moles of water, which is what we're after in this particular part of the problem, to 1 mole ammonium nitrate. So we're using a 2-to-1 ratio here to turn moles of reactant into moles of product. Then we'll multiply by the molar mass of water, which is about 18 grams per mole, 18.02 grams per mole. So after we canceled the grams ammonium nitrate, we're going to cancel the moles of the ammonium nitrate. We then got moles of water. Moles of water cancel to get grams of water. 204 grams of water should be produced by that 454 grams of reactant. 204 grams is called the theoretical yield because that's how much we should be able to make. And we'll talk about why that's important here coming up. But if all goes perfectly well and we don't spill any chemicals or contaminate it, or I don't drop my coffee in there or something like that, we should be able to get 204 grams of water from our 454 grams of ammonium nitrate. There's another product, though, in this problem, dinitrogen monoxide, N2O. And to figure out how many grams of dinitrogen monoxide you could get out, you could do the grams, moles, moles, grams dance one more time. You'd start with the 454 grams ammonium nitrate and turn that into moles, and you've already got the molar mass. The ratio between ammonium nitrate and N2O would be 1-to-1. So you'd have equal moles N2O to moles of NH4NO3, and then you'd multiply multiply by the molar mass of N2O to figure out how many grams there were. But in this particular problem, there's another way to do it, because law of mass action, law of conservation of mass, says all the mass that goes in, i.e. the reactants, equals all the mass that comes out, i.e. the products. So in this problem, 454 grams is how much we put in, and we just calculated that we're going to get 204 grams of water out, and you can see that those numbers are not equal. So whatever the N2O is going to be, it's going to be equal to 454 minus 204. Total mass in minus grams of water is going to equal N2O. This is an alternate way to figure out the N2O. Now, honestly, I would usually go grams, moles, grams for N2O, and I encourage you to check that out. However, this is an easier way, as you can tell, if it works, and we'll talk about that more later. So while 204 grams was the theoretical yield of water, 250 grams is the theoretical yield of N2O. We should be able to make that much N2O using 454 grams of ammonium nitrate. In this problem, the reason I'm kind of hedging my answers and why I say I usually go grams, moles, grams, is that we're using what's called stoichiometric amounts, perfect amounts of reactant and product. There's no excess at the end, left over or something, and it honestly is kind of a rare occasion in chemistry, and I'll show you examples of this here coming up. But anyway, it is an example if you have one reactant, definitely, it's breaking down into a couple products. This way works really well, but there's some times where this method won't work as well, and I'll talk about that more in a little bit. This is a summary of what just happened mathematically, all right? Now, the ammonium nitrate we put in was 454 grams, and although I didn't show the calculation, if you take 454 and divide it by the molar mass, you'll find that you get 5.68 moles of ammonium nitrate, okay? And that's how much we started with. So at the end, we're assuming that all the ammonium nitrate is gone. That's the minus 5.68. But in the process, we end up making 5.68 moles of N2O and twice that moles, 2 times 5.68 moles of water. The ratio of N2O was 1 to 1 ammonium nitrate, but to water, if you remember, it was 2 moles of water for every mole of ammonium nitrate. That's why we multiply it by 2. So at the end, you have 11.4 moles of water, twice as much as the N2O 5.68. And if you multiply those mole amounts by their molar masses, you get 250 and 204 grams. And by the way, that little dot by the 0 shows that it's a significant number. So that's a 3 sig fig value, 250. If you wrote 250 without the dot, it would be like plus or minus 10, 240 to 260 grams. But 250 with a dot would be plus or minus 1, like 249 to 251. That's the sig figs we want. So because the mass that goes in, 454, equals the mass that comes out, 250 plus 204, mass is conserved. And we're not breaking any thermodynamic laws or anything like that. Pat yourself on the back, thumbs up. Pretty cool. This is kind of a general plan for doing these stoichiometric coefficients, and you may find this useful, you may not, but here's the punchline. At the middle, the core of all these problems is going to be the mole-to-mole ratio that comes from the balanced equation. That's the stoichiometric factor, all right? And you may be going reactant to product, product to reactant, reactant to reactant, whatever, but that ratio, that factor, has to come from the balanced equation, and that's why it's so important. Now, what we've been doing so far, we've been taking grams of something, turning it into moles, moles of the thing we started with to moles of what we're looking for, and back to grams again. That's the grams, moles, grams. But you can go even farther from that if you want to. We'll talk about things, ways to go to volume using what's called molarity. We could take the density of the substance and turn the grams into milliliters. You could even use Avogadro's number to turn moles into number of particles using Avogadro's number, 6.022 times 10 to the 23rd. But again, you must have a balanced equation or all of this stuff doesn't make any sense.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces gaseous oxygen and water. The hydrogen peroxide is oxidized and reduced at the same time. It undergoes a disproportionation reaction. The manganese dioxide serves only as a catalyst and is not consumed in the reaction.
If you've ever purchased H2O2 hydrogen peroxide from the store, it always comes in a brown bottle. You're supposed to keep it in the refrigerator, stuff like that. And the reason for it is that H2O2 will decompose. It decomposes into water and oxygen using that reaction right there. And notice the stoichiometric factors, 2 H2O2s make 2 waters and 1 oxygen. That's kind of the idea. Now, if you want to speed this along, you can use what's called a catalyst. We're going to talk more about catalysts this quarter, but a catalyst is a chemical that makes the transformation happen much quicker than it would have been otherwise. A catalyst is something that makes the reaction go faster, but it's not used up itself. And manganese 4 oxide, which this lame video called manganese dioxide, but anyway, manganese 4 oxide is a better name. It will actually break down H2O2 a lot faster than it would have been. So you can see it's pretty exciting when you put MnO2. And the cool part is you could, in theory, just evaporate the water that's left and you could reuse the MnO2 again. You could have it in another catalyst, stuff like that. But anyway, that's beside the point. I'd like you to try this problem on your own. This is a grams, moles, grams problem that's very similar to what we just did with ammonium nitrate. In this problem, we have 5 grams of H2O2, and I'm curious what mass, grams, of O2 and water you can obtain using this amount. So I'd like you to find the theoretical yields, if you will, of water and O2. How you would start this problem, you'd start with the grams of the H2O2 and turn it into moles of H2O2. Then you have to pick water or O2, doesn't matter. Let's do water first, I guess. That would have a ratio, according to the balanced equation, 2 moles H2O2 on the bottom for every 2 moles of H2O on the top. So that would be how you go from the reactant to the product. And once you have moles of water, you could multiply by the molar mass to get grams of water. When you do the oxygen, you could do start it the same way. Grams, 5 grams of H2O2 to moles using molar mass. You would use 2 moles of H2O2 on the bottom for every 1 mole O2 on the top. When it's moles of oxygen, then you multiply by the molar mass of O2 to get the grams of O2. If you did this correctly, here are the answers. So again, try it yourself. You should get 2.35 grams of O2, 2.65 grams of water. So that's the answer you should get. Try it yourself. And if you can't get it, of course, let me know. I want to be able to help you. If you can show me what you're doing, I can try and help you out with different things. Notice how at the end in this problem, if you add those two product amount up, you do get 5.00 grams. All the mass that goes in equals all the mass that comes out. Pretty cool. The theoretical yield is the maximum amount of yield that should be created by a particular reaction. So in the last example there with ammonium nitrate, we calculated the grams of water that should come out and the grams of N2O, stuff like that. But what happens a lot in an actual chemical reaction is that you end up losing some. This reaction has a lot of gases, and it's easy to let like a stop cork or something open up accidentally and some of the gas escapes. Or maybe there's another chemical around that one of the reactants or products reacts with. So the percent yield is an important concept. Percent yield is nothing more than a ratio between the theoretical yield, which you have to calculate, and the actual yield, which is how much you actually collect at the end of the reaction. And people usually multiply this by 100%. So I have seen chemists trying to create the same chemical but with different mechanisms, like they'll have different reactions. And they will say, well, yes, your method's good, but my percent yield is higher, so my method must be cooler, these kind of things. It's amazing. But anyway, percent yield is a nice way for chemists to compare their reaction pathways and see if there's like a better way to make the particular reaction. So the actual yield should be less. There's 1 or 2 exceptions when it can be higher, but that's never good. Anyway, actual yield is usually less and stuff due to things like not reacting all the way, which is something that happens. Maybe it's a difficult reaction. Maybe, again, you let some out accidentally or spilled some. I mean, these are all legitimate things. Chemists are human, just like everybody else, and all these things can happen. But a percent yield is helpful. Usually, as you do a reaction more times, your percent yield gets better because you're more used to the system. You get better results. So just kind of think about that as we go through these sections. Let's say in the last example, we were supposed to get, theoretically, 250 grams of N2O. Cool. But for whatever reason, when we did the reaction and we tried to follow the instructions, etc., we only got 131 grams of N2O. All right? That's the actual yield. And again, why we got less, I don't know. You'd have to be in the know of the experiment to figure it out. It doesn't really matter. But we can use this information to calculate the percent yield of N2O. So percent yield is actual over theoretical. So for this problem, that would be 131 divided by 250 grams. Notice they're both 3 sig figs, so we're good to go. Multiply it by 100%. 52.4% yield. So the yield of N2O, 52.4%. And again, it's hard to know what that means. Maybe it's really good, maybe it's really bad. It's easy in academia to think that, well, 90% and higher would be a good yield because that's an A, 80 to 89 would be an okay yield because that's a B, whatever. All right, don't think that way with theoretical yields and percent yields. I once had a percent yield of about 4%. Yes, that's right, 4% of a compound. It was a purple compound. And I was so thrilled. I called my parents. I was in a different time zone at the time. I said, hey, I made the purple stuff. And they're like, it was the middle of the night, right? And they were like, oh, okay, you need to get some sleep now or whatever. But anyway, it doesn't matter. I was the first person who ever made the purple compound. So 4% was pretty cool. All right. Now, as I did it more times, I was able to make that percentage get a lot higher. It never got to 52%. It was very air sensitive and water sensitive, so it was really easy to contaminate. But anyway, regardless, the percent yields, you have to know more about the experiment to know if that's a good yield or a bad yield. Here's another reaction that I'd like you to try yourself and see what you get. This is just a way to test yourself. This stuff is super important to chemists because, again, this is how chemists get paid, remember? So it can be kind of cool. So in this problem, we've got a sample of copper 2 sulfate. We have 1.274 grams of it, and it's reacting with an excess of zinc metal, and we actually get 0.392 grams of copper. So notice that that's the yield that we received. It is not the actual amount that we calculated. So I want you to calculate what the percent yield is going to be here. And there's the equation. So how you would answer that is you take that 1.274 grams of copper 2 sulfate, turn it into moles, use the molar mass. Then for every 1 mole of copper 2 sulfate, you're going to create 1 mole of copper. So in this case, the moles are equal to each other. You can then take that moles of copper, multiply it by the molar mass of copper, 63.546 or whatever. That'll give you the theoretical yield of copper. And I guarantee it's going to be a number less than 0.392 grams. So the percent yield is actual over theoretical. 0.392 grams is what you actually got, divided by the amount of copper that you theoretically calculated, the theoretical yield, times 100%. Good to go. Here's the answers I got. The theoretical yield of copper was 0.5072 grams. And again, I got that from grams copper 2 sulfate to moles copper 2 sulfate, 1-to-1 ratio. So moles copper 2 sulfate equals moles of copper. I then multiplied by 63.546 to get the grams of copper, the theoretical yield. So the percent yield would be the actual 0.392 divided by the theoretical yield 0.5072 times 100, 77.3% copper. And again, try this yourself. Make sure that you're hip with this kind of process because we're going to do a lot of this.